Today I'm gonna present our results about the analysis that we performed last year, almost last year, and that we learned a lot, how to use OpenFOAM, how to generate the CAD geometry, how to perform the verification and validation analysis. And the thing is that we were kind of hired by the Ecuadorian Navy to analyze one of their submarines. This is a submarine that was built at Germany around 40 years ago. Is still operating, and they keep upgrading their equipment in regular basis. So this submarine is around 60 meters long, and they were having an issue. I don't know if you can see this red like device in here in the center photo. So that's a speed probe. And the thing is that the submarine used a device in order to estimate their position when it's operated underwater. And GPS is not working there, and they have to rely on this tiny device in order to be safe. And this submarine has two probes, this one on the side and one that is covered here on the upper deck section. And this was a real challenge for us. We haven't performed any analysis about underwater vehicles. So we started with our previous experience about analyzing surface vessels, and we started looking for answers about how these position estimation works when the submarine is underwater. So we found that there are a lot of options that surface vessels use. Typically, they trust on the GPS, as all of us do. But when the submarine is operating underwater, you got no signal for the GPS. Just imagine underwater, 40, 50 meters under the free surface. So they have to rely on several kinds of devices. The one on the bottom are quite classic, standard, old too. And one of the modern one is this electromagnetic sensor. So this is the one that the submarine use, basically, because it's more reliable. And the thing is that this probe needs to be placed on the hull where the water flow is basically free of vortex structures, no air bubbles around, the flow is continuous, and especially it always has to be wet because it generates an electromagnetic field, and it measures the velocity in terms of the electrical signal that is generated inside that electromagnetic field. And the thing is that although the manufacturer said that you can place it anywhere on the hull, they don't tell you exactly where. And they said that all the possible nonlinear hydrodynamic difference between the hulls due to the curvature can be overcome after a calibration, a proper calibration. But the thing is that these standard SAT trials, sea trials, they're good for surface vessels, as in when the submarine is operating close to the surface. But what I found, or what we found, is that this calibration procedure has to be performed also for deep water operations. but their calibration relies on the measurements performed on the surface condition. And it's kind of confusing at the beginning, but the thing is that the flow condition between these two navigations, they are not the same. There is extensive evidence that the flow change, um, especially the resistance force has nonlinear effects, nonlinear behavior. When the submarine is close to the free surface, for the DARPA, there is extensive experimental data, as the one that I showed you on the right-hand side below, for a submergence of 1.1 times the diameter of the submarine. The DARPA is like um, submarine that was developed by the US government in order to provide data for the CFD specialists for their validation. I'm trying to understand the flow around a submarine that is not, doesn't have any military use. So all the information about this submarine is open source. I think that is quite easy to get if you are not in Ecuador, of course. So we start with analyzing this DARPA submarine, trying to learn how to perform reliable simulation. And after that, we went for the real full-scale submarine, the 209. So we use the version 7 of OpenFOAM. We follow the guidelines of the ITTC. Our solver was Interphone, the PISOS solver, and K omega turbulence model, plus wall functions. That's a standard for surface vessels. So we started from there. And our first step was to understand how we can complete grid convergence analysis for the full-scale submarine without having any experimental data to validate our results. So, as I said, we started with the DARPA submarine I'm showing now the grid for both submarines, on the left for the DARPA, on the right for the Type 209. And you can see that they are quite similar. They got 6 refinement levels through TopoSet. And after a while, we decided to extend our analysis from 3 grids densities to 5 grid densities. So for the DARPA, we went from 200K to 11 million elements. And for the 209, we went from 500 to 22 million. We were lucky enough um, to get access through a HPC facility. And after our verification and validation studies for the DARPA, the grid convergence for the 209 submarine, we choose the grid number 2, that it was our fine grid, that showed that we don't need to go extremely high count elements. So we analyze 3 conditions. As I mentioned before, the sensor, the speed sensor, is used for the near free surface conditions, like the one in the middle, but it's calibrated with the first condition. And the second sensor, the second probe that is on the upper deck, is calibrated using the second condition. So it's all connected, and we try to assess what is the difference between the flows between all these 3 conditions. For this, one of the problems, or one of the challenges that we have to overcome, was how do we get a smooth Prince layer distribution along the whole structure, the whole submarine hull. And the thing is that this submarine, the curvature is high and is complex, especially when the main hull intersects with the upper deck superstructure. And even we try to cover the whole submarine should be red. What we got, the best approximation that we got is the one that I'm showing you on the left upper side. And for the surface condition, we consider it was good enough for now. We need to improve that in the future. And we double check it with the Y plus distribution along the hull. So we performed the verification and validation for the DARPA. As you can see, the resistance force, it converge really fast. It's easy to converge, especially because the condition that we are considering here is, it could be labeled as deep water condition. HD 5.4 means that we are really far from the free surface. So we don't have any oscillations on the force, converge steadily, and we got a good percentage of grid convergence index, especially for the finer set of grids. We see that we are below the 1%. So we consider that we validated for the DARPA, although on deep water condition. Right now we are working on validating, performing the same analysis, but the condition that is closer to the free surface, to 1.1 depth. But I would say that we plan to publish that on the next OMAE conference, if they accept our abstract. So after we performed that validation, we run several cases for different depth conditions. 5.4, it's far from the free surface. 1.1 is the closest that we can get experimentally. And although we are not on top of the experimental data, we are quite close, especially on low fruit numbers. And what we are doing now for the publication at OMAE is making sure that this behavior is not just luck, that we get lucky, but we are performing additional simulations in between just to confirm that our setup is able to capture this nonlinear hump when the submarine is operated at 1.1. So I think that by next week, we should have those results. So once that we trust on our setup, we used it to analyze the 209 submarine. Because we didn't have any experimental data yet, we performed a grid convergence, again, using the 5 grids with different, from 500 to 22 millions. And we considered we got convergence, grid convergence. Although if you compare this resistance force evolution with the DARPA one, you can notice that at the end, after 10K iterations, there is still some sort of oscillation on the resistance force. And we do believe that this is due to wave breaking on the bow of the submarine. Of course, we are planning to perform some sea trials, but due to the COVID, that was supposed to happen last year, and they rescheduled it for June this year. So we are really looking forward to that sea trial, and we hope to be involved. So talking about the 209, this surface condition, it behaved basically as a surface vessel. We confirmed the wave train along the submarine, the wave profile. We saw that there are two wave systems, one that is generated at the bow and a small secondary one that is close to the aft foil that in this condition slightly pierce the free surface. We compare the pressure, the dynamic pressure distribution. We got what we expect about. We got some acceleration region, almost around up to 20% of the length. And after that, we got a distribution that corresponds to the wave train that we show at the upper side. And the wall shear stress, this is quite interesting. We notice that there is some sort of a scar along the hull that propagates downstream, and we believe that those are vortex structures that are generated due to the wave breaking system that we got on the bow, like around here, the wave break, and after that, the eddies is propagated downstream. So definitely that's not, we should avoid that region in order to place our speeds prof, the sensors. An additional step for us was important to assess how the velocity, the flow velocity, changed along the hull. And we use the dynamic pressure distribution through Bernoulli. We estimate the velocity outside the boundary layer. And we notice that this gray dot corresponds to the position of the side prof. And we now know that this sensor, although is on the acceleration region, this is between a flow velocity above the navigation velocity between 1.1 and 1.2. And this distribution remains constant for all the operational velocity of the submarine. This distribution corresponds to the fruit number almost 0.2. If I remember correctly, that was like 9 knots. And we got we can get a good idea about how the velocity goes to 0 at the stagnation point to the value, the navigation value that is almost orange, really close to the middle section of the hull. And of course, that velocity distribution is also affected by the wave system that we got at the free surface. We use the standard procedures to identify the vortex cores, the parameter Q and lambda, and we detect that there are some big structures close to the wave that generates at the bow, upstream of the bow of the submarine. And this is propagated downstream along the hull. So we should be, we believe that the speed sensor on the side, it's gonna operate in almost ideal condition, at least for this surface condition. And we try to assess if there is a difference between two different kinds of prof. The one that I showed you at the beginning is the protrude prof that is almost 50 centimeters long, but the ship owner was considering to change it for a flush prof. That is basically a dish that you place it on the hull, and it measures the velocity almost at the same level of the hull. So we found that it shouldn't have a big difference if we use any of those prof. The velocity is almost the same with a slight variation for the protrude one. But if we see how the velocity, the flow velocity change in all the range from 0 knots to 9 knots of the submarine, we can see that in the place that the ship owner put their sensor, it keeps the linear behavior. That's some of the requirements that the sensor manufacturer ask. And as a sanity check, we also compare our force coefficients with the ITTC predictions, that is the black square. And we see that because we generate a grid based on the higher fruit number, we got almost an exact match for that condition. But once that we use smaller fruit numbers, that predictions is not that good. But we believe that is due to that those lower fruit conditions get less elements along the wavelength and along the wave height. So this is something that we can live with for now. We are looking for ways to improve it. And as a reference, we place also the experimental data from the DARPA. Of course, that this is the total force coefficient. And our submarine should be above the force coefficient from the DARPA. So at least we are on the same order of magnitude. That's good. And next, we wonder what happened when the submarine start to submerge. So what is the free surface influence on the flow field along the hull? So this condition, it was our near free surface condition, the periscope depth at the same fruit number. And we noticed that a wave train is generated, especially close to the sail of the submarine. And it's propagated downstream, but also because the main hull is quite close to the free surface, we also have some a weak wave system that is generated due to the hull. If we compare it, of course, that we can set that at the surface condition, it behaves like a surface vessel. And when it's at periscope depth, the main parameter that we should take in account is the distance between the sail and the free surface, because this is the dominant wave system that is generated. So after that, we compare how the velocity field change due to this free surface proximity. And we noticed that the main hole between the periscope depth and the deep water depth is not changing a lot, but the one distribution that changed dramatically is the one on the sail. And that makes sense because it's the closest structure that is near the free surface. So the velocity distribution changed a lot. On the deep water condition, you can notice the stagnation area on the front, and you can see an acceleration region that is generated downstream. But when we compare it with the periscope depth, this distribution changed a lot. So we got the conclusion that the procedure that our Navy is using now about the calibration from both probe sensor, using the surface condition is not safe for them. So we proposed to change some stuff on their calibration procedure in order to include this free surface effect. And especially because they have two probes. The one on the side is the blue line, and the one on the upper deck is the red one. And you can notice that the slope of both lines is different. So that is showing us that both sensors are in different regions of velocity. The upper side probe is basically measuring the actual navigation velocity, but the one on the side, it got around 15% higher flow velocity. So it's not safe for them to perform that calibration and use them, especially if they stay more than, I would say, 2 or 3 hours submerged. So I hope that we can fix that in the future. As a conclusion, we were able to assess the flow along the hull, the pressure distribution, the wall shear stress. We were able to visualize vortex structures, and there is dominant, especially due to the wave breaking system at the bow. And we need to rethink the calibration procedure, especially at deep water conditions. What's next? We have been working in this problem for the 2019, I think. We have a lot of things that we could improve, but right now we are working on verifying the effect of the boundary layer thickness on the speed measurements. And this is something interesting because we are naval engineers and we are looking at our problem through the hydrodynamics part, but the speed sensor is an electromagnetic, use an electromagnetic field. So we need to cooperate with, especially from a completely different area, in order to assess what is the effect that has the boundary layer thickness on the measurements that the probe reports. So we plan to do that this year. And of course, I'm really willing to be part of the sea trials on that submarine. It's gonna be a navigation around, I think that 100 miles. It would be interesting to share that experience. So if you're curious about additional details about our setup, results, we got a recent paper on the Fluids Journal, and we are preparing one of the manuscripts for the OMI conference, if they accept our abstract again. And so, gracias. And if you have any questions, I'm happy to answer.